Welcome to APA's Facility Symposium and today's session entitled COVID-19, HVAC Conversation with ASHRAE. My name is Billy Zydik, Standards and Codes Administrator, and I will be serving as your moderator for today's program. I'm going to turn it over to our speakers in a minute, but before we get started, I wanted to cover some housekeeping basics and the flow of the content today. We will be recording the session and posting the recording after the event concludes. All attendees are in listen-only mode, and as such, we will be using the chat feature throughout the program unless your presenter calls for open mic. We do ask that you be mindful to ensure your mic is on mute when you are not speaking in order to minimize interruption. Please use the chat box function to enter any questions you may have. We will be monitoring the chat box throughout the presentation, and we'll have time to address your questions at various moments during the session. If at any time you experience technical issues with visual or audio, please also use the chat feature to bring it to our attention. It is now my pleasure to welcome Corey Metzger, Founding Principal of Resource Consulting Engineers, and David Handwerk, Assistant Vice Chancellor for Facilities at Arkansas State University. Gentlemen, take it away.
Thank you very much. I appreciate the opportunity to be here. I'm Corey Metzger. I'll start off with a presentation. Just for reference, I'm the schools team lead for the ASHRAE Epidemic Task Force. We are focused on K-12 and university or higher education facilities. So coming with that perspective, I've got a 36-slide presentation that I'm going to get shared here. And I am going to try to get through it in 30 minutes. So I'm going to go quickly on some of the slides. I'll try to get a little more in depth on others. Can everyone see that okay? Hopefully. If don't hesitate to interrupt me if for any reason you can't hear or see anything okay. So I'll get right to it. Our learning objectives for today are to explain the basics of the SARS-CoV-2 virus and transmission pathways, describe guidance documents that have been produced by ASHRAE. I'm focused on this reopening schools and universities document. We're going to talk about some of the others as well. Understand some of the specific suggested strategies to mitigate airborne viral transmission of the virus, and then review some potential updates to guidance that may be coming and some potential changes to design strategies. I'd like to briefly acknowledge a number of folks who have been instrumental in the development of not just our team's guidance, but the Epidemic Task Force guidance in general. Bill Bonfleth is our chair, Dennis Knight is our vice chair, and Wade Conlon is leading the building readiness group and has been participating kind of across the board with multiple teams. Rick Hermans was actually the first lead of the schools team. He's moved on and is now leading a research group, and I had the distinct, I think, privilege of taking over as the lead for the schools team. So as I mentioned, there are a number of other teams. We'll talk about some of those as we go through the presentation here. There are also a few groups, ASHRAE TC 5.5 being one of them, that have provided some additional guidance more focused on specific systems. So we can talk about that if there are any questions. There are a number of resources available. So the kind of overarching or umbrella document would be the building readiness document. It talks about buildings from a general standpoint. We have a schools and universities reopening guidance document that I've mentioned a few times already. There is a filtration and disinfection document, another very thorough, detailed piece of information. Multifamily document, healthcare, commercial, transportation, and we have some more coming, including laboratories. We also have an air cleaner, one page on in-room or terminal air cleaners, and we've got some other updates coming. I share this because obviously the audience here has a different group of facilities to deal with and to cover than many facility managers or owners do. You've got just such a broad group of facility types that really all of these probably apply. to some sort of or something you cover on your campuses or for your organizations. So quickly, the virus, I'm sure you've all seen hundreds, if not thousands, of pictures of it. I'm not going to talk about the virus in a detailed way. I will say, compared to presentations that I did earlier in the year, we do feel like we've got more detailed and more mature information coming out on research. We're able to maybe make some better decisions on some of the things that are available now. Obviously, there's more coming every day. We know that early on during the pandemic, there was a real focus on mitigating transmission through social distancing, cleaning of surfaces, use of PPE. That's still prevalent and most certainly should be. There was a slow willingness to acknowledge the potential for airborne transmission by some key organizations, including the WHO and the CDC. Fortunately, they are now acknowledging airborne transmission as a legitimate concern. I think the level to which they acknowledge those concerns maybe still could be adjusted or improved. There are a lot of things we don't know. We don't know what exactly the viral shedding rate is. We think that it depends on individual people. Some may shed at a higher rate than others. There's likely a difference for different activities, likely a difference for potentially even different genders or ages. We don't know exactly what the infectious dose is. Again, that may depend on the person or the age of the person or other factors. We don't know what percentage of cases are being transmitted from each pathway, whether that be airborne or close contact or fomite. We aren't sure what that is. We believe that all three of those at least are major transmission pathways at this point. We don't know where the virus goes when it's airborne. We can talk a little more. I don't have details in the presentation, but there have been studies that have shown or have found virus DNA. So not necessarily, it's unknown whether the virus was infectious or not, but virus DNA downstream of final filters in a healthcare environment. There have also been studies that found viable virus about 17 feet away from a patient in an airborne infection isolation room in a hospital setting. We don't know what the best air distribution strategies are, and that likely depends on the space type and space occupancy and a number of factors. There are a lot of people working on that, but we'll talk about that in a little more detail as well. So I mentioned the schools team that I'm the lead for. We have a pretty large group. I want to highlight just a few people real quick. Dennis Knight, who's the vice chair of the Epidemic Task Force, has also been participating in the schools team with us. We have a few others that have been very active. Raj Sethi and Keith Hamelman have presented with me on a number of cases. And I don't mean to leave anyone out because we've got a great participation from the rest of the group. Down at the bottom there, Wade Conlon and Kathleen Nolan are technically not part of our committee, but they have participated in a meaningful way. Coming from their groups. The other thing I'd like to highlight is our breadth of engagement from across the country and in fact around the world. We have Frank Mills from the United Kingdom participating. We have engagement in Canada and from all over the United States. So we're fortunate to have a good diverse group working on that guidance that we're working to develop and update and continue to improve. So we've got some important assumptions that I want us to look at. First of which is that occupant health and safety is the focus. Energy efficiency is obviously important. We don't mean to ever write that off, but it's considered secondary at the moment to occupant safety. Social distancing and PPE should always be used to the extent possible. We certainly recommend following the requirements of the CDC or OSHA or your state public health department, whoever the cognizant authority might be. Similarly, with cleaning protocols, we recommend following the recommendations there. We are not trying to be everything to everyone. We want to focus on the things that we can help with, which is really your HVAC systems and buildings and how those can mitigate spread. So we would like to make the assumption that buildings have code-required ventilation. We know that's not always the case. We'll talk about some steps that could be taken in spaces that are occupied without that a little bit later. And we'd also certainly like to make the assumption that there are means for control with every facility. Now, again, we know that's not valid either, or that the means for control could vary significantly from on-off control with pneumatics or some electric controls to a fully capable DVC system with lots of trending and alarming capabilities. So we've got the document that I've mentioned a few times. There's a link here. There was a link earlier as well. We are on our third iteration of that document that was posted on October 7th. We're working on some updates for a fourth iteration. Each one has been fairly minor, but we've made some changes as we've moved forward. We know that some of the information we issued initially may have been excessive as far as suggesting full outdoor air all the time or running systems 24/7. Those were, the best initial response we thought we could make, but as more information became available, as we sat back and evaluated the guidance that was provided initially, we determined that there are some steps that are probably not providing significant benefit, but may have significant drawbacks, such as excessive energy use. So we issued this document within weeks of starting it. Typically, to issue something for ASHRAE, it takes years. So we're doing our best to make this the most useful information it can be, and we do feel like there's a great deal of good usable information, not just in this document, but in others. But we also recognize that there's opportunity for improvement, and we're going to keep working to do that. A few of those things that we're working on with that improvement, we have core principles that are being reviewed for all of the documents, not just the schools and universities guidance. So the building readiness document and the commercial and multifamily and all of the others are being reviewed for that. We're also looking at a shift to heating. When this guidance was originally developed, not to say we ignored heating, but we were really focused on the coming cooling season. And I think it's recognized now that we're into heating season, if not already there, we're getting close. So working on that. Again, the last item here is that this is really focused on HVAC systems for buildings and how we can mitigate with HVAC systems. It should always be stressed that we can mitigate, we cannot eliminate risk with our systems or with any other step other than keeping people apart. So some key concepts in that guidance. I'll go through this very quickly. We've got checklists in the 42-ish page document that's available right now. Those checklists cover maintenance and operations. We want to look at verifying HVAC system design so we can understand that we do have adequate ventilation, that the systems are capable of maintaining adequate indoor environmental conditions, and that we know what system capacities are if we want to make any changes. And then we want to take that review of the design and make sure that the building's actually working the way that we think it is, because oftentimes as I'm sure you all know, they don't necessarily behave the way we hope they will or expect them to over time. So that could involve retro commissioning, it could involve calibration, sensors could involve some testing and balancing, could involve some minor control tweaks to be able to more effectively trend and alarm in spaces where things may not be working quite right. Those are all steps that can be taken. We can talk about them in more detail, but I want to make sure we get through key concepts here. So some of those key concepts are ventilation and flushing of the building. We know that by bringing in outdoor air, we can remove potentially contaminated air in the building. Looking at increasing filter efficiency, so we may not remove viral particles from the building in this strategy, but we can remove them from the airstream. So another potential path for reducing risk in the space. There may be minor control sequence modifications that can come into play as part of this, so that adding of a sequence to flush the building or to adjust how demand controlled ventilation operates are things that could be limited scope changes to incorporate that can be done fairly quickly. And then there are a number of other possible improvements, including filtration units, portable or terminal in-room units, humidification, some other air cleaning or purification or treatment technologies. We'll talk about all of those just a little bit. So detailed strategies that we're going to look at. We'll start with ventilation and flushing. So we're basing, as I mentioned, everything on the assumption that we've got ventilation in accordance with ASHRAE standard 62.1 or your applicable local code. We know that's not always the case, but the code is really the minimum that we want to target. The reason that we're looking at that, and this is a theoretical calculation, you can find a number of calculators online. I'm happy to share some information on those. But looking at providing clean air to a space with a number of people in the space and somebody that's infected, the potential for transmission drops significantly with the higher air change rates of clean air, as you'll see here. When we get above 6 or 8 air changes of clean air, the potential for transmission drops significantly. The different colored lines are based on different quanta from the Wells-Riley equation. There are a number of values that have been proposed for quanta. It's used for calculating airborne transmission for viruses or any airborne pathogens, I guess I should say. So we're assuming outdoor air is clean in that statement. One question to ask is, can that be recirculated air? We'll talk about that in a few minutes. And again, I'll talk about or we'll share some information on calculators if anyone's interested in seeing those. So with that ventilation and flushing strategy, one of the things we want to do is look at a daily flush between occupancy periods. So if there were a buildup or a high concentration of viral particles that are aerosolized in a space, we can get those out. So the goal is obviously to remove contaminants. Our current guidance suggests a 2-hour flush period. If you look at a building readiness document, they're going to tell you 3 air changes of outdoor air or 2 hours. And the reason for that is that many buildings, if they are meeting, particularly if you have classrooms or laboratories or other space, they may not need 2 hours to hit that 3 air change rate of outdoor air. And the whole goal of that 3 air changes is to remove 95% or greater concentration of contaminants within a space. So obviously doing this is likely to either involve schedule changes or control sequence modifications, potentially both. And you certainly need to look at system capabilities, especially as we move into the heating season and the peak of the heating season. There may be implications of trying to run this flush between occupancy. You know, if you've got buildings that are occupied till 10 p.m. starting at 6 a.m., you're talking about absolute peak heating with full ventilation. So looking at increased ventilation, I'll talk through this quickly. This was something that we pushed hard initially, still would certainly recommend considering increasing ventilation where appropriate. We are certain that it will help to dilute contaminants. In most cases, obviously, we need to understand the quality of the outdoor air, but the chances of having high viral concentrations in outdoor air are very low. So initially we said 100%, 24/7 if you can. Now we're saying get to code at a minimum, increase it where it's feasible and appears to be appropriate. We want to look at equivalent air change rates for clean air now. So the system capacities that your systems are capable of need to be considered. If we run into a situation where we try to run 100% outside air and it freezes a coil, now we've just disabled that system and created a much worse case than we would have had otherwise. So we want to limit those increases to maintain indoor air quality. Certainly, as we looked at the cooling season, the potential for many places to not have adequate dehumidification became a concern. We're recommending disabling demand-controlled ventilation wherever possible. That needs to be considered carefully. It needs to be done in a way that makes sure spaces receive adequate ventilation. So if you have systems designed with no diversity, then we'd suggest adjusting your carbon dioxide set point, assuming that's the control point that you're using as a surrogate for occupancy, to something close to ambient carbon dioxide levels. And that should drive your demand control ventilation up to near full capacity. If you've got a system that uses diversity in its sizing, that may end up underventilating some occupied spaces. So we want to make sure that we're careful about how that's done. Just for reference, as we looked at cooling, and I have a heating chart, but I just can't help doing a presentation without a psych chart because I'm an engineer and it's just so much fun. This gives you an idea of what we're looking at for an increase in cooling capacity as we go from 20% to 80% outside air. You can see our load increases here. Oh, sorry. Our load increases here by almost 100%. And our sensible heat ratio in the cooling scenario drops from 73% to 48%. That's a significant concern for dehumidification inside of the building. So moisture is always a concern for indoor air quality. We don't want to grow mold and potentially create another hazard for people that may be infected with a virus that's attacking their lungs. So the demand controlled ventilation item I mentioned, just want to make sure your system isn't designed with diversity if you just apply a change to the CO2 set points across the board. In the case where it is designed for diversity and you do that, it's possible that the spaces at the end of the system become are starved of outside air and are underventilated, and those may be your most occupied spaces. So there should be some consideration given to how that's applied. That's true for any of the strategies we're talking about. I just want to make sure that this one's clear. Air distribution and flow rate. This one is, I have one slide on, I'll make it quick. We don't know the best, as I mentioned, the best distribution strategy for most spaces right now. So the assumption has been to go with a well-mixed space. Then we at least know that we're getting air through the space. We also don't want to have a space where we're moving air from one occupant to another to the extent possible. We don't want drafts that move across the room. There are folks that are suggesting displacement ventilation is going to be the best long-term strategy for this type of operation. Others are suggesting that ceiling supply, low wall return is going to be best. Others think mixing will be better than either of the other two. I know there's a lot of CFD modeling, there's a lot of testing being done. We just don't have enough information to make definitive statements on that right now, from my perspective at least. And I think the reality is that even if we did, you couldn't change all of your systems in the time that it would take to deal with this, since we're already occupied in many cases. The one other thing that I want to highlight with airflow rates for your facilities that have variable air volume systems, if you think back to that graph I showed with the Wells-Riley equation and the reduction in transmission with clean air rates, if you reduce the amount of air, if we assume that the air coming from your air handler is clean because it's been adequately filtered, and we're going to talk about that in just a minute, but if we assume that it's clean and you have a VAV system that turns down its airflow, we've now reduced your air change rate, which potentially increases your risk for transmission. So there may be consideration that needs to be given to variable air volume systems and what's done with minimums, or how those systems function. You know, are they effectively diluting the contaminant concentration in space? So with respect to filtration, want to talk about the standards that we're looking at. So most of our recommendations are related to MERV standards, or minimum efficiency reporting value. That is based on ASHRAE standard 52.2. I'm going to reference 2017. There are a couple of things to keep in mind. Most facilities that we would be looking at, you know, typical classroom buildings or office buildings, or you know, not a laboratory, not a healthcare facility, would be in that MERV 6 to 8 range. What we're recommending now is targeting MERV 13 or better. So if we can get to that level, we can much more confidently remove a high percentage of the aerosols that would contain virus that might be moving through your HVAC system. And the reason for that, to look at this chart, which may describe it a little differently, and I have one more, and then I'll stop with the boring filtration stuff. I won't stop. I'll keep going, but I'll move on. Is that MERV 13 hits 50% effectiveness at removing particles in the size range of 0.3 to 1 micron. So the virus is about 0.12 micron. We know that. It's smaller than this, so why do we care about this effectiveness? The reality is the virus doesn't leave your body on its own. It leaves in a respiratory droplet with a little bit of mucus or a little bit of something else, and it ends up most likely being in the 1 to 5 micron range, we think. So as you look at that, you can see that in that MERV 13 and higher range, we start seeing pretty good effectiveness at capturing particles in that size range. Whereas at MERV 8, you might get 20%, right? Now, these are standard minimums that have to be hit. So there may be some cases where a MERV 11 actually does pretty well in the size range we're worried about, or a MERV 9 might do pretty well. So it's worth looking at individual filters, but I just want to have that for reference. And then from a graphical perspective, this really tells the same story I just told, but this is our, assuming that the virus was leaving the body on its own, this is about the particle size you'd see on this line here. So you can see that A MERV 8 is going to remove very little of the virus. A MERV 13, it's not perfect, but you're getting close to 40% removal. If you can get to a MERV 14, you're over 60%, right? If this were just the virus, and we know it's not, if you move over on those charts to that 1 micron size range and you follow this up, now at 13 and 14, you're really in a great spot as far as performance goes. Whereas at the 8 size range, we're still down in the 40% or less capture effectiveness. I should acknowledge this is from Kowalski and Bonfleth study they did in 2002. That is the same Bill Bonfleth, who's the chair of the Epidemic Task Force. So I mentioned our goal is MERV 13 or better. We want to, though, carefully look at where we're applying this. It shouldn't just be arbitrarily applied across the board. The outside airstream of a dedicated outside air unit may not need a filter improvement unless you've got environmental concerns to address. If you've got filter racks that are in poor condition and have significant leakage, increasing the filter efficiency and potentially the filter pressure drop that goes along with that might increase the amount of air that is just moving around the filters themselves. So that needs to be considered. The pressure drop that goes along with better filters needs to be considered. Filter types, we'll talk about that a little more in just a second, and then whether or not this is a central system or terminal equipment. So from a fan perspective, when you put better filters in, if they have half an inch of difference in pressure drop, and sorry for the fan curve, but again, I'm an engineer, I can't help it. So if we had this as our operating point and we tried to move up on this same fan curve for an extra half an inch of static pressure, we would run into a situation potentially where we cross this do not select or do not operate line. So we need to be careful about how that works. Many fans will have capacity to handle better filters. Not all will, though, and it needs to be considered. So there are a number of filter classifications. We focused on MERV because that's what's going to happen in most commercial buildings. HEPA is great if you've got a lab facility or a healthcare environment where you need HEPA. By all means, go for it. There are two differences between MERV ratings. There's MERV, which is the rating that we just looked at, and then there's MERV A. The only real difference there is that MERV A hits the filters when they're testing them with something that will dissipate any electrostatic charge, so it's a mechanical only filter. Some MERV filters are charged filters, and depending on how things are operating, if that charge gets dissipated, a MERV 13 might actually be a MERV 7 or 8. So something to consider. ISO or HEPA, looking at putting HEPA filters in most air handlers isn't realistic. You probably don't have means for holding them as far as filter rack goes. The pressure drop's going to be significantly more, that sort of thing. Looking at terminal equipment, fan coils, VRF, finding filters with MERV 13 or anything close may be very challenging. That needs to be considered. You need to look at how frequently you're replacing them. Again, if it's a charged filter, but it only gets replaced every 6 months, there may be a good chance that that charge dissipates during the time it's operating. Looking at how the system's configured, where's your outside air coming from, a number of things like that. There may be good justification for considering portable HEPA filters in that space. So with respect to room air cleaners, portable terminal HEPA filters, terminal filters, whatever you might call them, we are working on, we being the ASHRAE Epidemic Task Force, is working on providing a guidance document. That guidance document will tell you to use HEPA or a high MERV filter. You want to look at your clean air flow rate or clean air delivery rate if you're looking at a retail grade type filter. You need to look closely at sound and placement. We don't want to create drafts, again, between occupants. If it's in particular a classroom environment or an office environment, sound may be a problem. If these get turned down and don't operate the same airflow that we're selecting them for, that reduces their efficacy. So there is a good spreadsheet from some researchers at Harvard and University of Colorado Boulder that may be very good to consider if you're looking at something like that. One of the key things that I would look at is what kind of filters are you putting in these units? Are they proprietary from the manufacturer where you're always going to have to go back to that manufacturer? Or is it something you can get from any filter supplier? And then how many different unit types do you need throughout your building? So these are great tools to look at when you know you don't have adequate ventilation. we can achieve from a viral perspective, from an aerosolized virus perspective, we can achieve the same effect by removing virus from the air with filters that we can with outdoor air. It doesn't address other indoor air quality concerns, but at least for the current conditions, it's something that can make a difference. So I'm going to talk humidification. I'm going to do it quickly because I'm already, I think, approaching my time limit here. There have been a number of studies related to influenza that show significant drop-off in transmission, airborne transmission of influenza. We fully expect that, or many people expect that this would be true for our current virus of concern. There are some great resources out there. A couple of studies noted at the bottom of the slide. There's also a ASHRAE technical hour that can be seen from Stephanie Taylor, who's a member of the Epidemic Task Force that has really great information on it. Those are all, I think, useful tools to look at. There are a number of different types of humidification that can be considered. I'm going to go back real quick. The key thing that people are pushing for with humidification is hitting 40% relative humidity. You can see a significant drop off in the rates of infection between 30% and 40%. So you can look at central humidifiers, could be located in an air handling unit or duct mounted, portable, something that you set up in a room. Key things to look at are water treatment, potential for condensation in your space. So water treatment, when we say that, we're thinking Legionella. We're thinking other indoor air quality issues that could happen if there's some other contaminant in that water. So you need to be careful with that, not letting water sit for extended periods, especially if it's in the temperature range where Legionella grows. That potential for condensation, we're looking at the building envelope. So for reference, if you're in a climate that involves a lot of heating, at 70 degrees and 20% relative humidity inside the building, your dew point is 27.7 degrees. So if air moves from the building inside to the exterior, if the wall surfaces inside are below 27.7 degrees, you will have condensation. I guess I don't have another line here. For reference, if you hit 40% RH, now you're talking 44.6 degrees dew point. If you hit 60% relative humidity, you're up to 55.5. So you're going to see significantly more condensation in the walls. So while humidification has some significant justification, or at least some strong indicators that it may be a good strategy to reduce viral transmission, we don't want to do that. At least I would suggest you don't want to do that at the expense of growing a lot of mold in your walls and again, potentially creating significant indoor air quality concerns. I believe the last strategy I'm going to talk about are other air treatment technologies. So there are a number of technologies out there, including UV, including bipolar ionization, including photocatalytic oxidation, and others. They're generally targeting deactivation of viral particles. Some of them may also cause particles to agglomerate. I would very carefully look at the claims that are being made, or look for independent testing and standards. We know that, for example, UV germicidal irradiation is probably a little more widely researched and understood than some of the other technologies. I'm not saying they don't work, but I think you need to be careful about implementation. I would certainly avoid reducing ventilation air under all circumstances at this point. I think that would be an inappropriate step given everything we know today. So in summary, and again, I'll apologize for running a little long here, information is changing rapidly. We know airborne transmission is possible. We know systems need to work as intended to try to help mitigate the spread of the virus. Using ventilation and filtration as key tools, we can reduce viral concentrations in spaces, but we need to look carefully at any application that we implement. Humidification and other air treatment steps may be appropriate, but they, again, need to be very carefully considered. With that, I will turn it over to David and let him talk about some more specific implementation.
Thank you, Corey. And I know Corey popped up the slide that had the questions posted up there. We're going to do that at the end, allow 15 minutes for us to do Q&A and go over this. So a little bit about myself. I am an APA member. I am the Senior Facilities Officer here at Arkansas State University, responsible for 4.3 million square feet of campus building inventory and space. HVAC maintenance and capital construction is under my umbrella. I'm also an active member of ASHRAE. I'm on just rolled off the chair of a technical committee for education facilities, which Corey is on. And they asked me to be part of the epidemiology task group, but with everything we're doing, facilities getting prepared, I just didn't have time. And they had some good folks on there that had K through 12 and university experience, so they had those inputs. Kudos to them for the work that they cranked out. I'm also a member on ASHRAE, the energy standard 90.1, and of course, Corey's right. The energy conservation is important in these considerations, but it's definitely secondary to the health of our occupants. So I'm going to share screen and get the right screen put up here. I think that's the right one. Okay, everything is correct. You should be seeing my slides here, and it covers up. I got my other screen covered up. So if you got questions or things that you need to bring up as a chat, I can't see that chat screen unfortunately. But so I want to cover a lot of the same topics that Corey covered and relative to, but the operations side. How do we apply these best practices? And I want to focus them in some of the same categories that Corey covered. But and so I'm kind of repeating some of the things he's saying, but I'm looking at it from an operations and maintenance perspective of how really the challenges that we saw on our campus and some of the peers that I hear from, some of the challenges they cover with some of these strategies for making our buildings safe relative to the HVAC systems. So I do agree that we need to try to follow the MERV 13 recommendations at ASHRAE as a minimum wherever we possibly can. Of course, there's always things you need to really consider on this, and Corey brought this up. Not all of your legacy systems on your air handlers are going to be able to handle a MERV 13 rating. On our campus, we have air handlers that go back, several decades in age, and it's just a metal box, a fan, and coil. So, that technology hasn't changed, but the filtration on these have radically changed and the requirements for the filtration has changed radically over particularly the last 2 decades. So you need to consider that and make sure that you can meet that. And Corey covered this, but your filter frames and even your newer air handlers, if you're not got a tight spec on your campus, is basically going to be like a C channel or a U channel that your filters slide into. And there's no seals between the filter and certainly no seals between that U frame. I would say that doesn't even meet like a MERV 7 type of rating, but yet we have that as a standard, and you need to look and see if that's the situation. So most of these air handlers you cannot retrofit without going to a great deal of expense on that. So putting a higher grade filter in there, you may or may not get the actual rated filtration if you're trying to go to even a MERV 11 or 13. The pressure drop is a big issue that comes up between peers and as operating a campus. The first assumption is that if you go to a MERV 13, if you can do that, the pressure drop is going to give you a big hit. As Corey indicated on that fan curve, most of the time I would say that manufacturers and design engineers are going to overspec a fan in their ratings. And they do that because it's really no cost difference usually if you go to a bigger fan. So if you're going to design with a safety factor in place and then you put a safety factor on top of that, more than likely your pressure drop is not going to be an issue on your campus. And so that it's not going to affect your motor horsepower as far as tripping the motor. Now, I would say that that's not going to always be true. You may need to double check and see where your motor current ratings are already, and just have your technicians in the field just double check that before you considering the filter upgrade. One thing I would say is that we have places on our campus where airflow is maybe compromised. We're marginal. So you can, if you go a higher pressure drop, you're going to affect your airflow rate. So you may have marginal issues of cooling or heating if you affect that CFM. There's the big deal for going to a higher MERV rating on your filters is the additional expense, and it's going to have an impact on the operating budget. In our case, we have a filter contract that we've worked with a provider that provides a single source for all of our filters, and to just in time, they came and did an assessment and inventory of all of our air handling equipment, even down to the terminal type units with fan coils and mini splits and things of that nature. And they provide filters on a routine basis based off of our PM schedule. And we are traditionally, we're MERV 9 in most cases. I'd say about 70 to 80% as a standard. But we do have some MERV 11 out there in a few locations. To go from up to a higher MERV rating is a tremendous expense. So I'll talk about that here on the MERV. If you can't go to MERV 13, go to MERV 11. So I'll talk a little about expense here in a little bit. So one reason why I think that if you cannot do MERV 13, if it's not practical with your air handlers, and Corey showed it with his chart, when you get into the 1 to 3 microns, up to 5 microns, there is difference, but not tremendous difference between 11 and 13. And don't misinterpret what I'm saying is that MERV 13 is just as safe as MERV 11 relative to this virus. I think that Corey highlighted that there's a lot of research to be done of like, what does these droplet size actually do in the airspace? It could be in a certain humidity, especially lower indoor humidity, the droplets could be a change in phase, and then the droplets get smaller. So what does that do in suspension? I think it's the reason why you see when humidities are low, the transmission of viruses increases because they can stay suspended in the air longer, and plus they transmit further. But if you go to the 3 microns and larger, they're really close. You're 85% efficient, whereas MERV 13 is 90. And I think it's where we see the droplet size that we think from the current research and understanding of this virus, that a lot of that happens at that size level. So MERV 13 is certainly much better than 11, but if you can't get it because of your filter frames or other factors, MERV 11 would be, in my view, would be a good substitute. Same with the MERV 13, the filter framing is still an issue. You can go in those U channels, you're not going to get a MERV 13 seal if you just have a C channel or U channel with no seals around it. So those have to be the items that you look at in your facilities and see if you can upgrade that. The cost differential between a MERV 9 and 11, we priced that and said, well, let's just take all of our filters to a MERV 11. We'll worry about the seals later. And that was roughly for our campus about a 40% cost increase for our annual contract. And then I said, well, what would it be? I knew that we have very few cases where we can go to a MERV 13 because of our filter frames and other factors. It was over 100% increase in price. Now, we priced that when demand for MERV 13 was really, really high. And we think that was an impact, but we think that it's still going to be around double the cost to go from where we are to a MERV 13. And that's a pretty significant cost increase on our operating budget. Also, with any increase in air filter efficiency, because of pressure drop, you're going to increase your energy costs. But I think one way you can kind of offset that cost is you can go to a demand-based filter changes versus a scheduled filter changes. We've been planning for that for several years, but obviously you got to have some type of instrumentation in the field to do demand-based filter changes. And what I mean by demand-based is you measure a pressure drop and you say, at this pressure drop, we are going to change this filter. Well, there's a lot of logistics behind that. So there may be some air handlers that still have a quarterly or maybe a semi-annually filter change, and there's others that may be longer or shorter. And so how do you predict that? So that's one hurdle to overcome. Obviously, the instrumentation and tying that to our energy management system to get that feedback of when to change the filter is also a challenge. So we're working through that. But if you can do that, you can save costs I think that we are changing our filters much too soon. And one element is that filters become more efficient as they load up. And there's a point of diminishing return of that. So we change a lot of clean filters, and we change a lot of really, really dirty filters. So we've done an evaluation where we're trying to figure that out. I think that's one way to offset your costs for increased energy is if you can reduce your frequency of filter changes and do it by demand. Ventilation considerations, just really, again, supporting what the ASHRAE has said with ventilation. I think it's extremely important for our buildings that it's well ventilated. First, to get it to the 62 standard, that is really for most states, that's the code. That's what you need to ventilate to, is for safety. But when you're going out and looking, we need to survey and assess all of our mechanical and natural ventilation systems. Don't assume that you have mechanical ventilation everywhere. There is some natural ventilation that may be working okay, maybe well, maybe totally inadequate. Just kind of do that assessment and see what you have. A lot of campuses are not sure where they have ventilation in their buildings. And it may be that some office that only has this information. So find it, then you identify and prioritize all the deficiencies with your ventilation system. Again, supporting what Corey said, at least get to the code minimum to start, and then look at enhanced ventilation from there. But there's going to be systems that are operating off pneumatics. There's going to be systems where there's dampers not working. There's going to be systems where maybe there's dampers that was totally deactivated and the outside ductwork was actually sealed up. I found those on our campus, and I asked why. Well, we were freezing coil, so they just got rid of the outside air completely. So I thought, well, that solved the freezing coil situation, but now we created a new unintended consequence. So identify and prioritize those deficiencies. And I think for highly occupied or occupancy intensive buildings, that should be your first priority. Certainly housing on campuses is a high priority because they're occupied more hours during the day, and it's pretty intensive throughout the day, especially if you're like our campus that is face-to-face classes, but a lot of them are online. Most students are staying in their dorm rooms now more hours during the day, so ventilation in those spaces are a high priority. Then you can prioritize your deficiencies from easy to challenging to remediate, or challenging could be dollars. There could be some systems, like we have a building that's naturally ventilated. To put mechanical ventilation in is going to be hundreds of thousands of dollars. So I can't fix that right now, but I can put a budget together. But the easy ones are just getting dampers to work, actuators working, looking at your control sequences and getting those to work. Those are easy to remediate. Assign teams to do those strategies and execute from the priority scope. Go to those really, really high priority items and work down the list and work the list. We need to verify our ventilation system rates, and that's kind of like what I'm saying. Just see if you get it working, and then see that you're meeting ventilation rates for that's for that space or building. And if possible, you can calculate the air change rates. We get a lot of questions on our campus from our faculty, staff, and visitors that are saying, "What's your air change rates?" We have a large event in our basketball arena, and it's a lot smaller due to the physical distancing and other guidelines of our state health department. But still, it was pretty intense relative to the state we're in with COVID. And by the way, we're one of the red zones in the United States right now with possible positive cases. But they always ask, what's the air change rates from the fresh air? So if you can calculate that, you have that information, you can communicate. It's always good information too if you've got a low air change rate, that you figure out a way to remediate that. And sometimes remediation can be very challenging because you don't have the equipment there, the infrastructure to increase that air change rate. Survey and document their occupancy schedules, so that ties into the guidelines that you have additional ventilation post and pre-occupancy. So, the guidelines for ASHRAE is a couple hours. We're doing a couple hours for most of our buildings, pre-occupancy, if we know the occupancy schedule. And so if you don't know the occupancy schedule, you cannot ventilate that 2 hours or 1 hour. I would say if you're looking at purging a building, you should do the ASHRAE recommendation of 2 hours. But if there's circumstances where you can't do that, then at least 1 hour to get some ventilation to purge the building. Don't forget the post-occupancy as well. If you're not economizing, here's an opportunity where you can leverage your controls, especially on your more modern systems and your newer systems, to really get there economizing. You can get, in some cases, we found that we weren't economizing, and we can get like 50% of our air exchange in the building to be outside air. And when we have the dew points and the temperatures that are appropriate for economizing on the air side, we can do that, and we can report that to our occupants. I think you need to monitor for unintended consequences with these strategies, because sometimes you'll have, Corey mentioned the low and high humidity issues and condensation in the buildings. You can have poor outside air ventilation that you're bringing in unintended, pathogens or unintended contaminants. And then overheating and cooling spaces when you're doing this, just kind of monitor for the indoor air quality. And if possible, you can measure and document your energy costs, because it may come up that you can get reimbursed or supported by your administration or your institution or your company to get reimbursed from that if they're seeking assistance from other sources for covering the additional cost of this COVID. You need to develop some capital plans for adding ventilation on your buildings where you have to do those major improvements. UV light, I'm going to touch on this as well. I'm a big fan, have been a big fan of UV lighting on air handlers for a long time. We've kind of waned before COVID of putting UV light into our systems, because when we had new buildings, it tended to be one of those opportunities for value and de-engineering, taking it out. But I've seen the before and afters of keeping coils clean, and I'm in a climate zone where we have to cool and dehumidify several months out of the year in the Mid-South, close to Memphis, Tennessee. So sometimes we have 75-degree dew points for 8 to 10 weeks of the summer. So UV light is a good factor for keeping cools clean for mold, but it's also been proven to be very effective on the COVID virus and other pathogens. And it's the UVC light that's really effective. So you need to know there's a difference between UVA, UVB, and UVC, and it's the wavelength. I think it's 253 nanometers of wavelength on UVC. So make sure that if you're talking to a provider that you're looking at UVC, if your goal is to address the COVID pathogen. So the UV requires three things. It requires intensity, the light intensity. It requires time, contact time, and it also requires proximity. So a lot of these are the time, the intensity, time, and proximity are all related, interconnected. So it's really important that when you're looking and considering UV, that you're talking to a provider that really considers that. So if you have one lamp that's in a ductwork, and you got an airstream that is going past it at 20 feet per minute, or however fast it's going through that ductwork, 20 feet per second, that it's not getting the intensity, time, and the proximity necessarily, unless it's well designed for that. So you got to be very cautious that you have a system that is designed for air handlers, sometimes these off-the-shelf will work, especially the smaller terminal units. You can use the smaller lights that are appropriate for residential systems, maybe fan coils. But for air handlers, it typically has to be a design system. So work with a provider that understands that. You need to understand that as an owner and purchaser. And you always got to remember that UV is the safety consideration, because it's damaging not only to viruses, but anything that is a living thing or can be like filter media, can be carbon-based products that can deteriorate or break it down. So you got to be careful for your safety of your workers and your occupants with UV light. And that's real important. I'll talk real quickly on bipolar ionization. I'm not as familiar with that, but I've done some research, and I know it's a proven technology in the food industry for a long time. But you're seeing that it's very effective on killing the SARS, COVID-2, and other pathogens. But depending on the application, where one advantage it may have over UV lighting, research I've done, the total cost of ownership could be less. First cost may be higher depending on the application, but it's case by case. But definitely one thing to consider. More research is needed on that to see how effective it can be on COVID, though. In most cases, the retrofit can be more cost effective on the bipolar, because the systems I've seen that is promoted, we don't have any on our campus, but you basically attach it into the airstream on the side of the ductwork. You don't have to go deep invasive into the system and put an array of light fixtures in there. If it's not a viable solution for small equipment terminal units like fan coils, but where UV may be more cost effective. Some other considerations to kind of go over: in-room purifiers on our campus was a hot topic for a lot of our faculty, and they wanted to put them in classrooms. And it's not a great holistic solution. I don't think they're proven that they'll work very well in small spaces, and that's really where their application shines. I think the task group looked at it for K through 12 schools, and a lot of classrooms are smaller classrooms, are in there long periods of time, so that while it can be running, you have multiple of these units in there. But for a university, it just is not a cost-effective solution for us holistically. I think there's case by case that the university said, yeah, it'll work. And most purifiers have a HEPA filter and a UV light in it. You can get an option with just HEPA filter that will filter the room, but it's basically going to circulate the air around that unit, so it's not going to circulate a large space, large volume, and I don't think it'll turn over the air in the space. So don't misinterpret. They do work, but they might not be effective in larger applications. I think that one thing that you can do as an owner, I think you need to have kind of an eye, what I would call an appearance of what you're doing, so everybody sees what's happening, actual events. So if you see a technician cleaning a supply register or return grills, they see that as making the building healthier and safer. It may not be necessarily doing anything relative to SARS and other pathogen type of remediation. It may get rid of mold spores that may be growing on your registers, but I think it's just one thing your occupants can see happening as an event. I think you need to prioritize really a deep cleaning of your air handler, especially in your major air handling equipment, in your occupancy intensive areas. We're doing that. We're going through and just doing a real deep maintenance cleaning of that, and even reaching up into the ductwork where it's appropriate to do some duct cleaning. I think we need to, as on the campus, when people are seeing maintenance workers practicing their face coverings, their hand hygiene, physical distancing, and surface disinfecting, I think it sets a signal that, hey, we're committed to this. Parts of the country, it can be controversial whether or not the people should be doing these things, but I think it's proven. If it's not, I tell folks, if it's not important to wear face coverings, the next time you get a major surgery, insist that your doctors and practitioners don't wear face masks while they're operating on you. I think that putting it on the terminology of how does it affect me if others don't wear masks, I think makes kind of stresses the importance of wearing face coverings. And it shouldn't be politicized, but developing the staff protocols is really important. If you have an infected space, what do your maintenance technicians need to do? If we have to go into a space that's been immediately affected, do they have the proper PPE, and have they been fit tested for respirators and other type of equipment? Have they been trained to wear it and take it on and off? So I think that's really important for knowing when you're operating a campus. Make your staff safe, but it's protecting your staff, but it's also sending a message to the rest of your campus and your occupants that, hey, we understand the risk and we're taking the right measures to be safe for our staff, but also safe for occupants. I think you need to educate your occupants of what you're doing. a lot of times we do these best practices and we're not telling what we're doing, and people are left guessing, is our building safe? So we need to promote the good stuff. Tell them what you're doing. And if you're not doing it yet, just say this is what's planned, and then follow up with a message that you've done this for your buildings. I think you need to evaluate for your construction standards, bring everything up to MERV 13 filtration. We're going to certainly do that on our campus. MERV 13 is a requirement, I think, for LEED certification. So good filtration, good indoor air quality starts with clean air. And so I think this is a given. But you ought to think about the integrated air purification strategies, whether that's, the UV or bipolar or other things. You need to develop your budget adjustments because your operating budgets are going to increase with some of these strategies. And I think that we're in this for the long haul, so you need to kind of plan for future years. You need to be monitoring, be educated with the post-COVID codes and standards upgrades. So we're going to see it happen. We saw with any crisis, in the terrible tragedy of 9/11 dramatically changed how we do structural design for especially high-rise. So we know that there's work already in place of updating our standards and codes to help address mitigation for future pandemics, and hopefully we don't have another one for a long, long time. But it's one of those things we can't predict, so we have to be prepared for. I think there's an opportunity for this crisis to develop innovation. So I think we need to be monitoring all the innovation in the HVAC world, but also other areas. I think APA can help with this, and certainly ASHRAE too. I think for both of these, where you're monitoring for codes, we have in APA, the Standards and Codes Council, that we're going to be more focused in the future of being a reporting and advocacy group, but also we'll be educated on HVAC technology. Obviously, that's the ASHRAE world. I want you to know that APA and ASHRAE have a memorandum of understanding where we work together, and we're trying to make each association more value added to their membership by bringing what strengths that each organization has. So look for that in the future as an APA member or an ASHRAE member. We need to be diligent. All these best practices are good, and we reacted quickly when the crisis hit. We can't let this fall down and say, once we get into 2021, maybe it's Q3, Q4, and things starts getting back to whatever is the new normal. I think that we need to recognize these best practices are best practices for a reason. So let's be diligent and be very disciplined that we continue these best practices to make our buildings safe. So this is our new normal. That's all the questions I had. So I'll stop the share and we'll open up for Q&A.
Right now, we don't have any questions in the chat box.
It's because Corey's that good.
You're both that good. Okay, well, if we don't have any questions, I would like to thank both Corey and David for taking time out of their busy schedules to do this presentation for us. I'd like to thank our attendees for taking the time to attend. So if we have nothing further, I'd like to wish everybody a happy holiday season and be healthy, stay safe. Until next time, have a great day. Bye-bye now.